Namaste and welcome to the second week of lectures on mathematical foundations for machine learning. In the last week we looked at the idea of vector spaces, subspaces. We basically looked at the idea of fields. Then we said how are we going to construct vectors using field elements, and then what kind of operations happen on the vectors, which includes vector addition, scalar multiplication, and then linear combination of vectors. Then we looked at a collection of vectors which obey these properties like scalar multiplication, closure under scalar multiplication, and closure under vector addition, and existence of zero vector in the collection. We call that to be the vector space. And then we said that not necessary that you need to look at the entire vector space. We said that okay, let's look at a sub collection of this vector space which obeys the properties of closure under vector addition and closure under scalar multiplication and existence of zero vector. We said that even a subset of the vector space which obeys all these things turns out to be a vector space. We gave a name for it. We said that look, such subsets which are vector spaces themselves, you call them to be the vector subspaces. And then we also looked at the geometry of the vector subspaces. We said that in case of 2-dimension or 3-dimension or any higher dimension, we said that line passing through the origin is a subspace. Then we said planes passing through the origins are subspaces, and so on. And then we had a couple of questions like what is it to combine vectors, like how do we combine vectors. We looked at the linear combination of vectors and so on. And then we also looked at the idea of linear independence, and we said that okay, like I have vector space which has infinitely many vectors. Now I have, my problem is like to find out what happens if I try to transform whatever that transform actually means. We said that what happens if you try to transform the entire vector space, like how do we study the effect of transform on all the vectors in the vector space. So for that we said what is the strategy that you would like to adopt or you would want to adopt or what we should be adopting. And that is where we got into the idea of basis for a vector space. We said that okay, basis is nothing but a set of linearly independent vectors whose span is going to cover the entire vector space or probably a subspace. So if you know what the transformation does to the basis vectors, you know that what the transformation does to the entire vector space. That is what we said, but we really did not touch upon like what it actually meant. And then we said that look, okay, we had bases, and then we said that there could be multiple bases for a vector space. And then we also said that okay, the number of linearly independent vectors or the number of vectors in a basis, you call that to be the dimension of the vector space, and so on. Now the key question or the key idea that we looked at in that week's lecture is that how do you study the effect of a transformation on all the vectors in the vector space or the entire vector space. So the question that we need to ask now is like what do we mean by a transformation, like how do we even, without even knowing a transformation, how is it that we say okay, look what's transformation doing to the entire vector space when it does not make real sense. So we need to figure out what is this transformation, what kind of transformation are we talking about. We are going to look at in this week, the focus will be on linear transformations, and we will also be looking at the idea of eigenvalues and eigenvectors. Linear transformations are extremely essential and important concepts as far as not just linear algebra is concerned. The application of linear transformation is quite huge if you look at right from the idea of computer graphics to physics to data science to almost everywhere you have the ideas of linear transformation being there. So the question is, what is a linear transformation? How do we define linear transformation? Can we take some examples and then see what actually is a linear transformation? Can we look at some example transformations that we have? And then we will look at the idea of eigenvalues and eigenvectors. So the focus of this week. So let us begin this. So our focus this week is going to be the following. Week 2, we have linear transformations, and let us say eigenvalues and eigenvectors. Okay, so the question that we tried answering from the last week is like, okay, what is it to say that there is a transformation of all the vectors that is happening? So, what do we mean by transformation, and how are we going to mathematically capture it, and what is it that we are going to say in terms of the properties of linear transformation, so on. So, that will be the focus of this week's lecture, and let us get on to the idea of linear transformations now. Okay. Okay, so what does this mean? The idea of linear transformation is basically the following. These are some kind of mapping between vector spaces. So, let us say these are mappings between vector spaces. Right. Now, should these mappings obey certain rules? Of course, yes. So, these mappings they obey the rules of vector addition and scalar multiplication. And scalar multiplication. Okay. Now, what does that mean? Let us take some example. Let us motivate our idea of linear transformations from examples, and then probably look at the mathematics of it, right. So, what we do is, in this case, we know, like from our high school understanding of mappings, we say that, okay, suppose I have a function. Let us take this, consider for example, let us take this, consider this function. Let us say y is equal to x squared, right. Now, what does this function do? This is basically, I will say y is equal to f of x is equal to x squared. Now, what does this function do? It basically takes inputs it basically takes some number as input, and then the output of this function is going to be the square of whatever input that we have given, right. Say for example, suppose you take x is equal to, let us say, minus 3. Therefore, y is equal to f of x is equal to minus 3 the whole square, which is going to be 9. So, what it does is, it basically takes certain inputs, it is going to give you certain output. In the same way, we could actually look at matrices, right, as, say for example, now let us look at the idea of let us take this entire idea of y is equal to x squared or this mapping. Let us study this from the perspective of matrices. Now, consider, let A be a matrix for our specific, for a very simple example case. Let us say A is a 2 by 2 matrix. Let us take A to be a 2 by 2 matrix. Now, what does this matrix basically do? I have this, which is, let us say, A11, A12, A21 and A22. These are my matrix elements. This matrix basically takes input, which is x given by x1, x2, and then it outputs this vector, which is y1, y2, or let us say we normally use this term, this notation, we will say B is equal to B1, B2, right. Now, what does that mean? Suppose I have this, I have the matrix A, which is basically given by this A11, A12, A21, A22 into the input is going to be my vector x1, x2. So, the output is going to be, let us say, B1, B2. In the sense we see this B1, B2, the B vector that we get, this is a 2 component vector. We know the idea of, we know the meaning of what 2 component vector is, and in the last week we also saw 2 component vectors, 3 component vectors and so on. You see that the input in this case is a 2 component vector and the output in this case is also a 2 component vector. So, now what we have is, here is a matrix which operates on a 2 component vector to give me a 2 component vector. That means this matrix is going to change this 2 component vector or map this 2 component vector to get me another 2 component vector. So, I can write this as B1 B2 is equal to A11 x1 plus A12 x2 and then A21 x1 plus A22 x2. So, this is what I have, right. So, given a matrix A and given an input vector whose components are say x1 x2, the output vector that you are going to get is basically B1 B2, which is given by A11 x1 plus A12 x2 and A21 x1 plus A22 x2. Let us consider certain interesting examples. So, examples. The first one, let us take the matrix A to be this 1 0 0 1 and let us take x is equal to x1 x2. So, what is Ax is equal to? Ax is equal to, we have 1 0 0 1 into x1 x2 and we are going to get the right answer, the B vector to be x1 x2 itself, right. So, in this case our B vector B1 B2 is nothing but x1 x2 itself. That means this matrix A, which is given by 1 0 0 1, acts like a transparent door wherein which I have x1 x2, my x vector to be the input and the output is also going to be say x1 x2, right. And this is basically a transformation. This matrix that I have is basically, what it does is, it does something called as an identity transformation. What it does? It takes the input, the output is nothing but no change in the input, it just outputs the input as the response itself. Is that clear? So, this is basically an identity transformation. So, basically what it does, it maps the vector x1 x2, the x vector to itself, right. So, let us look at that. So, what does this matrix do? This matrix basically, if I draw it geometrically, let us see what happens. Suppose I take this let us say x1 and x2, I have 1 2 3 4 5, 1 2 3 4, let us say 1 2 3 4 0 1 2 3 4 and 5. What I have is, suppose I take my input vector x to be this, let me take x to be 2 3, 2 3 is basically this vector which is here, this is 2 comma 3, and if you pass this as an input to this matrix, this linear transformation 1 0 0 1, the output is also going to be 2 3, right. The output is also going to be 2 3. Therefore, what happens, we see that this is going to get mapped to itself on the operation of 1 0 0 1, right. Excuse me. So, that is basically your identity transformation. So, it is going to map the vector to itself, right. Let us take a second example, example 2. Let us take the second example where we are going to look at this. Let us take this. A is equal to 1, let us do this, A is equal to 0 1 1 0. This is what I am going to have 0 1 1 0. Now let us see what this transformation does to any vector that we have. So suppose I have my input vector, let us do the same thing. I have this transformation which is 0 1 1 0. I have my input x which is equal to x1 x2. The output is going to be 0 into x1 plus 1 into x2. So that I am going to get x2, and then the second component is 1 into x1 plus 0 into x2. So I am going to get x2 into x2 x1. So this transformation does something interesting. What it does? It swaps the two rows of a vector of a matrix. Okay, two rows of a matrix. Now, but geometrically what does this do? Because we are now dealing with the geometry. So what does it do geometrically? So let us understand what it does. I have, let us say, same x1 x2. I have, let us say, 0 1 2 3 4 5 1 2 3 4. Let us take input vector which is basically 3 comma 1. This is my input vector that I have. So I am going to give this 3 1. I am going to see what is this transformation going to do to this vector 3 1. So this is going to give me 1 3. Now where is 1 3? Let us see where 1 3 is. 1 3 is going to be here. So this is my vector 1 3. Now what has it done? This is basically trying to it has swapped the positions of the two rows of the matrix. It has basically swapped the two rows of the matrix, but has it done something else interesting? Yes, of course this has done something interesting. What is that interesting thing it has done? Let us look at this. Suppose I assume that I place a mirror here along the line 1 comma 1 2 comma 2 3 comma 3 4 comma 4. That means I am going to place a mirror about y is equal to x, at y is equal to x. I am going to have a mirror. Now what does this mirror do? We already know what a mirror does. The mirror is going to reflect. That means the mirror is going to do, I mean, whatever appears as left is going to appear as right, and whatever is right is going to appear as left once you reflect. That is exactly what we see here. Suppose if I take 3 1 and then give it to this mirror 0 1 1 0, it actually gives me 1 comma 3 which is some kind of a reflection, which is actually a reflection that it is done. So what we do is we are going to say that this 0 1 1 0 is basically a reflection transformation. Reflection transformation. Now what is interesting is this reflection. Now you can place the mirror wherever you want, right? In 2 dimensions you can place the mirror wherever you want. You can place the mirror not just at y is equal to x, you can place the mirror along any line passing through the origin. Accordingly the coordinates will change. Now what we have done is we have basically kept the mirror along the line y is equal to x, and therefore whatever was y turned out to be x and whatever was x turned out to be y here. In this case whatever x1 was there, that turned out to be x2 after the transformation, and whatever was x2 turned out to be my x1 after the transformation, right. So basically what it does, now I am going to say this 3 1 gets mapped to 1 3 by this transformation 0 1 1 0, right. This is interesting. Now let us take one more case. Let us take another example. Let us take example 3. Let us take example 3 where I am going to take the matrix A, the A to be this 0 minus 1 1 0. I am going to do this and I am going to say, look, I have my input vector x1 x2, the two component vector x1 x2, which is given as an input to this transformation, let us say 0 minus 1 1 0. The output I am going to get is x1 into 0 minus x2. So, I am going to get minus x2, then I am going to have x1 into 0 plus x2 into minus 1, the next one is going to be 1 into x1 plus 0 into x2. So, I am going to get this. So, it is going to be x1 into 0 minus x2. So, I am going to get this. Again, let us see what happens to this geometrically. So, we want to look at the effect of this transformation on the vectors. The transformation that we are going to look at is A is equal to 0 minus 1 1 0, and for this case I am just going to take two simple vectors, two interesting vectors, because I want to figure out what are these two vectors getting transformed to. So, I will take 1 2 3 4 here along the x1 axis, and along the x2 axis I have 1 2 3 4 here, and this is the 0 vector. So, let us take that is the origin 0 comma 0. Now, what I do is I take this vector, which is basically the 1 0 vector. So, this vector is basically 1 0, and I am going to take another vector here. Let us say the other vector is going to be this guy. This is going to be the 1 0 vector that I have. So, this is going to be my 1 0 vector. That is the 1 0 vector that I have. Now, what I am going to do is I am going to see what is the effect of this transformation on the 1 0 vector, and this is 0 1 vector, sorry, this is going to be the 0 1 vector, yeah, and this guy is 0 1 vector, and the blue guy is 1 0 vector. So, let us see what happens to this. So, let me take 0 minus 1 1 0, and I pass this vector 1 0 here. I am going to get the first component to be 0, the second component to be 1, and I am going to have this next vector 0 1, which I am going to do here. I am going to get 0 minus 1 1 0, and that is going to transform this vector 0 1. What is it going to do? It is going to take, you are going to get 0 into 0 plus minus 1 into 1, which is minus 1, 1 into 0 plus 0 into 1, which is 0. So, basically what we see is something interesting. What is interesting stuff? This blue vector now takes the position of this black vector. That means the 1 0 vector is now got shifted to the 0 direction of 0 1 vector, and that 0 1 vector that we had here, that 0 1 vector which we had here has moved here to minus 1 comma 0, right. Let us see what has happened. Let us basically look at this. I had my 1 0 vector here. This 1 0 vector got transformed to the 0 1 vector by this matrix 0 minus 1 1 0, and then I had that 1 0 vector which was here, the original 1 0 vector which was here, and that moved to my 0 minus 1, the minus 1 0 vector. So, this is the direction to which it is moved. This is interesting. Why? Because whatever was there along the x axis has now got shifted to y axis, and whatever was along the y axis has now got shifted to the negative x axis, right. So, you had along the x1 axis, the vectors along the x1 axis now got shifted to the vectors along the x2 axis, and all the vectors in the x2 axis now got shifted to the negative x1 axis. That means you see that it has rotated every vector. This transformation basically has rotated every vector by 90 degrees. So, we are going to say that A is equal to 0 minus 1 1 0 is basically a rotation transformation that we have, rotation by let us say 90 degrees, right. This is what we have. Let us take another example, so that once we get an idea about all these examples, we can now formulate the proper math of it, right. Let us take example 3, another example where my A is going to be this. A is going to be, let us say 1 1 0 1. right? I am going to look at A is equal to 1 1 0 1. I want to see what is the effect of this transformation on the vectors, right. So, if I take any vector, let us say x1 x2 and I apply this transformation which is 1 0 0 1 1 1 0 1, I am going to get the resultant vector to be x1 plus x2 and x2. That means the x1 coordinate changes to x1 plus x2 and the x2 coordinate remains as such. There is no change in the x2 coordinates, that is what we see here. Let us take an example and see what it actually means, right. Let us take, I just want to mark some point here before we okay, let me take this 1 2 3 4 5. So, let me take the 0 1 2 3 4 5 6 7 and 8 1 2 3 4 and this is my x2 axis, this is my x1 axis. Something which we would have seen, like let us I mean all of us would have seen it at some point of time. Let us try to understand what this does. Let me take a simple case in which I will mark, I will take up this. So, I am going to look at the transformation of all these vertices of this alphabet T. I am going to look at this, what happens to the vertices of the point of the alphabet T under this transformation 1 1 0 1 and see if I can actually make sense out of it. So, I want to see what happens to all these points when I transform using this particular transformation that I have, right. So, for that what I will do is I will put all these points as inputs to this matrix 1 1 0 1. What I am going to do is, you know that it is going whatever that you are trying to do is basically this is my x, this is my a and this is going to be my ax. So, what I will do is I will put x as, I will list out all the points that I have put here, let us take that to be the x and see what happens. So, this is going to be 2 0 2 2 1 2 1 3 4 3 4 2 3 2 and 3 0. So, these are the points that I have. So, I put all these guys into this matrix. So, what I am going to do is I am going to do x. So, this is the first vector, it is going to transform, then the second one, the third one and so on. So, I am just putting it in terms of a matrix and let us see what happens here. So, when I do this I basically get this, we already see that x2 does not change. So, I will put all the x2 as the same 0 2 2 3 3 2 2 0. What happens to the x1 coordinate? X1 coordinate is x1 plus x2. So, I have 4 2 3 2 4 3 7 3 6 2 5 2 3 0. This is what I have, right. I just need to add all of them and then I am going to put all these guys together, right. So, this is going to be the resultant that I have. Let us mark all those points that we have here on the same graph that we have, right. So, the first thing that I notice is 2 0 2 0 remains as 2 0, then I have 2 2, this point has basically moved here to 4 2, then I have 3 2 3 2 became 7 3 3 2 became 7 3. So, this is what I am going to have here. This 3 2 point became, so I have 2 2 3 2. Oh, so I have to look at this, sorry, I have to look at this particular point. This point is 1 2, 1 2 became 3 2, 2 2 became 4 2, yeah, 2 2, this point, sorry, this point 2 2 moved here and this point 1 2 moves to 3 2. So, that is the next point that I have, right. And then what happens? I have the following 3 2 4 2 4 2 3 2, then 4 3 I have 4 3 is here, 4 3 basically this 1 3 became 4 3 here, right, 1 3 became 4 3 and 4 3 became 7 3, 4 3 became 7 3, right, 4 3 became 7 3, that is going to be somewhere here, and then 4 2 became 6 2. So, let me put that here, and then 3 2 became 5 2. So, 5 2 is going to be here, right. So, and then 3 0 remained as 3 0. These are the points that I have. So, let us see how does this look like, maybe it makes some sense, let us see what happens here. So, let me join these two guys, these were already there, the base these two got joined, then I had to go here, 2 2 became 4 2, then 1 2 became 3 2, this is what I have here, 1 2 became 4 2, then I had 1 3 which became 4 3, then 4 3 became 7 3, then 4 2 became 6 2, 4 2 got transformed to 6 2, and then we had 3 2 which got transformed to 5 2, and then we get this. Well, that seems pretty interesting. Why? Because this transformation has basically changed the shape of the alphabet T that we have. The original alphabet was this. Now, what has this transformation done? This is basically tilted, there is some kind of a shear that has happened. So, this is basically called as a shear transformation. This is basically a shear transformation. This shears along the x axis. You also have shear along the y axis, which is given by the other shear transformation along the y axis is basically given by 1 0 1 1. This is also this is the shear along y direction. This is shear along x direction or x1 axis. This is shear along x2 axis. So, we have this. Now, where do we see this kind of a stuff? This is the most interesting stuff. This is like basically what you see in all your document processing, regular font to italics, regular font to italics, right. That means you can also have an inverse to go back to regular. So, you can find the inverse of this matrix and then get back to this. So, what we have seen is in all these cases, whenever you have a vector, you can capture a transformation in terms of a matrix, and the matrix is going to map the input vector to another output vector, right. Now, the question is, okay, we have seen some of these examples like identity transformation, rotation transformation, reflection transformation, shear and so on. Now, the question is, how do we mathematically capture general linear transformation? These are all linear transformations. So, we will see what it is to capture a linear transformation in a generic way. How do we put that mathematically, and is there something interesting that happens to, I mean you can, for example, when you look at y is equal to f of x is equal to x squared, there is something that happens there. So, suppose if you assume x to be the set of all positive integers or non-negative integers, you start with 0 and go on, y is equal to f of x equal to x squared will not have all the positive integers again. So, from the set of positive integers you give the inputs to be all positive integers, but the output is going to be not all the positive integers, but a subset of integers which could be expressed as x squared. That means now I have something similar to it, I can ask in terms of matrix. What is that? Suppose I have a transformation, do all the vectors get mapped to all possible vectors in the space or does it not? So, we are going to look at something similar to a range and other things for a function, and we are going to look at the analogous or the equivalent of range in terms of a matrix and a linear transformation. So, in the next class what we will do is we will try to generalize this idea of linear transformations, mathematically capture this, and then we will look at some interesting ideas like the range and the kernel of a linear transformation and so on. Thank you.